Okay, this time I'm going to talk about GSAS-II in particular. A couple of remarks about before I start. This was written because the old GSAS program had its limitations. It wouldn't deal with more than 99 powder patterns, or histograms as we call them, and no more than about 9 phases. And there were people whining about how it didn't deal with enough of either one of those. It was very difficult because of its design to expand beyond what it is. It was written in Fortran, which is fine, it's fast, but it wasn't a modern, it was no longer a modern program. Interestingly enough, the original user interface to GSAS-II was basically state-of-the-art in 1980 or 85 when we started it. But the art moved on, and it's now GUI programs. GSAS-II is written in almost entirely in Python. And you should know that it comprises about 150,000 lines of code. 3/4 of that code is for the GUI. 3/4 of the code is for the user interface. About 10 or 15% is the mathematics, and the rest of it is the graphics and I/O. So it takes a lot of work to write these things, I'd say. But anyway, let me start with the installation of GSAS-II, because this is something that people want to know. First of all, how do you find it? Well, if you just go on the web into Google or whatever your favorite search engine is and type in GSAS-II, and it can be either the Greek letters or the Roman 2, doesn't make the Arabic 2, it doesn't make any difference because it's the only thing out there with that name. And what you should see is this homepage website. And if you go there, it will give you instructions for finding installation kits and whatnot. And there will be installation kits for Windows, Mac OS X, and Linux. I might add, the problem with Linux, of course, is that there's a zillion varieties of Linux, so it will install on most of those, but not necessarily every last one of them. Sorry, but that's the nature of Linux, not GSAS-II. What will be installed will be Python, some libraries for Python, and GSAS-II will be a subdirectory in that Python directory. It will install anywhere. It will try to install in your private space, which means you should be able to install it whatever the administrative requirements are. Although in some places you can't even do that. And let me see what else I want to say right here. There are about 50 tutorials. There's more than 50 tutorials by now. The tutorials comprise something like 1.5 gigabytes of information, so we don't download that. You actually have to access it through the internet. And if you want a particular tutorial, it can be downloaded to your own machine, and then you can look at it, and what will come with it is the tutorial pages themselves and the data sets that go with that particular tutorial. Oh, I should say about install. You can install it anywhere, even on a memory stick. If it's a reasonable size one, something like 5 gigabytes. GSAS-II only takes about 1 gigabyte of memory to store it, something like that. One important point is don't use that directory for your workspace. Do your working directories somewhere else, not in the GSAS-II directory. And the reason is because GSAS-II updates, or you can get it updated, and if you put something in yours in that space, it might get overwritten. You never know. A key point is that we use what we call the continuous software development mode. In other words, we're updating it almost every day. If you get commercial packages like Word or things like that, the updates happen every month or a couple of months. We don't operate under those kind of conditions. We update as soon as we find something wrong or we want to add something to GSAS-II, we do it and upload the thing immediately, and you should download it basically as soon as you can. The current version is somewhere around 5,200, something like that. That tells you how often we update it. Okay. Okay, this is a modern program written in Python. And this is what the control tab looks like, or the control window. There's two frames and a console associated with GSAS-II. One of those frames is graphics. All the plots appear in that frame. The console is strictly there for information purposes. You can't input anything into the console, but it will give you error messages. And occasionally some information is printed out there rather than shown on the GUI page. This is organized in two sides. This side is the so-called data tree, and that's all the major items that are in your project. If you've got multiple data sets, they will all appear here as a string of individual, say, PWDR data sets. And you will learn the acronyms eventually, as the PWDR is for powder patterns, PDF is for PDFs, and so forth. Each one of these items has a number of sub-items, and we don't go any deeper than that. There's only one level of sub-items. And each one of these things describes a particular feature of that particular item. Phases are another block of information, and there could be multiple phases associated with it. There's no limit on either one. You could have 400 phases if you wished. I don't recommend it, but you could. But you can certainly have 400 powder patterns or 4,000 powder patterns. People have done experiments with 10,000 powder patterns in GSAS-II. It consumes a lot of memory, but so what? Disk memory is cheap nowadays. There is the menu at the top has two parts. Well, actually three. The first part is everything which is on the other side of this little vertical bar, and those items are fixed menu items. And one of the main ones that you should consider is the one that says compute, because that's where the least squares button is, the refinement button, which is under calculate. The stuff on the other side of that bar is associated with whatever is displayed in the window. And that menu bar will change every time you change the thing that you're viewing. This is associated with whatever you've selected on the out of the tree, and it will change completely depending on what they are. So if you want to look at the limits, you have to be in the limits tab in order to be able to see the limits on the powder pattern, for example. You won't find them anywhere else particularly. The data window contains all the information that's associated with whatever the chosen tab is. Now, things like phases have a number of sub-tabs, and each one of these things has a different window associated with it that describes that. It also has a different menu at the top. So things which are specific to the particular thing that you're looking at is what is shown to you. I've seen some other software where there's a whole double or triple row of icons, and I find those things terrible because you say, what the heck does all this mean? So we focus on exactly what it is you need to be able to do for whatever it is that you're looking at. So you do have to remember where stuff is, but we hope we've laid it out in a reasonably logical fashion. Okay, the plots. What we try to do in the plots is display anything that would benefit from a visual representation. So this includes certainly a powder pattern, where you get observed and calculated intensities, a difference curve, background curve, tick marks to show the reflection positions, and so forth. And by the way, you can move these things around under certain circumstances. So if you don't like the layout, you can change it. You can zoom in easily. So that thing works. Maybe it's because my finger's in the way. You can zoom in so you can see the details of the fit, whatever it is, it's useful. If you've got multiple data sets, you can create waterfall plots, which is the one there. You have control over the offset of each pattern with respect to the next one. So you can offset it to the right or to the left or up or down. And in contrast, you can create contour plots. This one actually shows the same information as that does, but this one is actually pretty clear that there's been a phase transition of some sort right about there. For drawing the structure, you can draw, obviously, polyhedra, as well as ellipsoids, or spheres, or balls and sticks, or just sticks, and so forth. For drawing the individual structures, you can also display a contour density through any plane if you've got a Fourier map. And this contoured map will change as you tilt the structure or shift it. It will always draw the map centered on that cross, which is the viewpoint that you're looking at. And it's always going to be in that plane perpendicular to that, in that plane which is perpendicular to the viewing direction. So if you rotate the structure, the map will shift with it. Okay. Again, the same kind of idea is that if you have a table of numbers, which here are the microstrain coefficients for this particular material, you get a picture. You can get a picture of what that surface actually looks like. Same thing with texture. If you've got a whole bunch of spherical harmonics coefficients, the coefficients don't mean anything to you. But when you display it, you can display it as a pole figure or an inverse pole figure. And you've seen the variance covariance matrix before. And by the way, you can zoom in. So if you want to know what this is about, you can zoom in on it. And actually, if you put the cursor on a particular box, that one, it'll tell you what the associated parameters are and the value of the covariance, in case you want to know what it is. Okay. As an aside, because GSAS-II is used to process two-dimensional images off of diffractometers, particularly the synchrotron, one of the things that we had to do was to find out how do you determine the orientation of the detector with respect to the X-ray beam. And this has been handled by a number of other programs incorrectly. In particular, Fit2D, which is a very commonly used, or has been a very commonly used piece of software for processing images. Well, it makes the assumption that the beam is at the center of the ellipse that you get. And you ask, well, where's the ellipse come from? If you look at it, if you think about a diffraction cone and you take a diagonal slice through it, the resulting figure is an ellipse. So the question is, where on that ellipse is the axis of the cone? It is not at the center of the ellipse. And Fit2D makes that assumption. Now, if the detector plane is perpendicular to the beam, it doesn't make any difference. But if that thing has a tilt, it makes a lot of difference. Now, Data Squeeze is another program that was written that makes a similar sort of an assumption, which is also incorrect. The correct analysis is 200 years old. By one G.P. Dandelin, who wrote in the Royal Academy of Brussels in 1822 the correct solution to this problem. And here's the figure out of his paper that I found on the web. The whole thing is in French, so I can't read it. But nonetheless, you can actually see his construction. Basically, you have the cone, and you put a sphere, a small sphere below the plane and another sphere above the plane. And the centers of those two spheres will define the line that passes through the center of the diffraction cone. And the rest of it is just geometry based on that construction. And GSAS-II uses this construction to work out where the beam is from a two-dimensional 2D image. Here's another sort of modern rendition of the same thing turned on its side, which is you have the detector plane, beam starts over that way someplace. Here's the sample position, here's the two spheres, and the beam passes through this point, which is the intersection between the two sphere centers. Now, how good is it? Well, in this case, to test it, I tilted the detector 45 degrees from the incident direction. And as you can see, the fit to the diffraction rings is absolutely perfect. If you fed this thing to fit 2D, it would fall flat on its face. It would not know what to do with it. So this was the test. Here's another test. This one, the detector is offset and tilted so much that the diffraction rings out here are hyperbola. Okay? And it doesn't calibrate out that far. This last curve here is probably really close to a parabola. You know, the sequence of conic sections goes ellipses, a parabola, and then hyperbola, if you think about how the intersection is. And as you can see, it integrates them perfectly well out in the hyperbola region. What this allows us to do is to use data into the corners of the diffraction image. You're not restricted to the center part of it. And it gets it basically absolutely correct. Okay, once you've done that, and you've created a powder pattern or a whole sequence of powder patterns, you can then go on and do the analysis of the pattern diffraction data, refelt refinement, indexing, whatever, are all staying inside GSAS-II. If the data image was a small angle scattering pattern, you can fit that inside GSAS-II. The powder pattern can be, excuse me, can be converted to a PDF inside GSAS-II. There's a little comment there about development and enthusiastic users. Enthusiastic users are always useful because they ask questions and point out errors. Okay. Peak, picking, fitting, and indexing. Basically, the peak fit routine uses the same peak shape function that I talked about this morning. It's the same one that's used for the refelt refinement, so it reports the same precision on the peak positions. And then the algorithm for indexing is the same as Alan Coelho's that it's in Topaz. It's basically the same algorithm. And it will then come back with a lot of possible solutions, and you pick the one with the highest N20 score, usually. Although sometimes that winds up describing, you can see some variation here between which way a monoclinic cell goes. Right. The only difference between this one and the one in Topaz is that this is a little slower because it's written in Python rather than, I don't know what Alan writes in C, an assembly language. Okay, so to do structure solution, I know we're going to be talking about it more at length, but the point is that if you have a powder pattern, and this happens to be, I think this happens to be sucrose, or maybe not, I'm not sure. You do a Pauli refinement, and I talked about that this morning, to be able to get a set of structure factors. And then you do charge flipping, which, by the way, is done without any reference whatsoever about symmetry. And that gives you a set of atom positions. And what GSAS-II tries to do is tries to locate the origin, obeying whatever space group you identified it as. It tries to shift the maps appropriately to get it in the right place. You then have to identify the atoms. Usually they sort themselves out as the biggest peaks are the heavy scatterers and the smaller peaks are the lighter scatterers. And so here's picking out the unique set of atoms, which happen to be closest to the origin. And then you identify what they are, and here's what the structure is. And by the way, this is not sucrose. That's something that's called kryptonite, which is an interesting material. But the atoms in here are sodium, silicon, boron. And by the way, the charge flipping found the boron atoms, oxygen, and somewhere floating in there is a hydrogen we don't see. Oh, wait a minute, that's a lithium, sorry. All right, now here's a different thing. This has to do with sequential fitting inside GSAS-II. And here's the experiment. This was done at the SNS down in Tennessee, at the VULCAN diffractometer, which is used for looking at engineering materials. And in this case, they had a stainless steel bar mounted 45 degrees to the incident beam. And what they did is they stretched it, shrunk it, stretched it, shrunk it. And they did that quickly 8 times over 13 hours, collecting a powder pattern every 1 minute. So there were 800 powder patterns. And here's the first one. And what we want to focus on is the positions of the first 6 lines in the powder pattern. And simply follow what happens to them as a function of this loading and unloading. So here's the contour plot of the 800 patterns generated as in GSAS-II. And you can see the first one is here, and you can see the slow wiggle first and then the rapid wiggling as the loading was changed. You can also see a second phase appears after many cycles of reloading. That's the so-called ferrite phase. But if you look very, very carefully at this line, there's actually a faint shadow of it even in the beginning. It's a little hard to see, but it is down here. Very weak, very broad. Okay, and so what happened in the process of doing this loading and unloading is it recrystallized the ferrite and made the crystals grow and become more obvious. The main peaks are from austenite, which is another phase of steel. So you did a sequential peak fit across all of these 800 powder patterns. It took a couple minutes to do, really quick. And then you get this table of values, which you can then plot as a function of time. And so this is the position of one of the austenite reflections. As you can see, it shifts back and forth, and there's a slow relaxation of it as the sample begins to fail from all the repeated loading. And you can actually sort of see it stretch out. If on the other hand, you track the intensity of one of the of 3 of these reflections, you can see there's a shift in the intensity of the reflections as a function of loading. And you ask, well, what's going on here? Well, what's going on is that there's a change in the texture of the material as you put the load on. There's a grain reorientation as it stretches, and then the grain orients back upon relaxation, and it rotates around again. And so that's actually giving you this change in the intensity. And if you look very carefully, they're actually not in phase. The 210 is out of phase with respect to the other 2. These little spikes down are when the beam dropped out. It's actually bad data sets. There's a lot of stuff one can do with this. So here's another case. This is now small angle scattering. And here's a typical small angle scattering curve. This comes from an aluminum polishing powder that was supposed to be bimodal. There's a peak here, and there's actually another peak here that's from the 2 different sizes of material in this. And it was advertised as 500 angstroms and 1 micron. That's around 10,000 angstroms. But in actual fact, the distribution is more like this, which is around 160 angstroms here and 1,600 angstroms here. So it's not what they advertise at all. And you can then also fit this to a model that has those as parameters. And this, by the way, is fitted. You can't see it, but there is a calculated curve that's under there, and there's a background. And I don't show the difference. Okay. And if you have multiple small angle scattering data sets, you can do a sequence of fits. So this is colloidal silica, which has been diluted. So there should be a shift in some of the parameters according to the dilution. There certainly is a change in the small angle scattering as you go from one to the next. And if you do a fit to the first one, you get that. And if you fit all the rest of them and then plot one of the parameters, you can see this nice straight line relationship between what was prepared and what was obtained. Once you've got that table, there's all kinds of analysis that one can do on the sequential fit data. And you'll have multiple columns of information depending on which parameters you actually refined. This works for Rietveld refinements as well as small angle scattering. Yeah. Some structures are not commensurate. In other words, the HKL positions don't describe a repeating reciprocal lattice. And what's shocking is how simple some of these materials are. This is sodium carbonate, stuff you buy in a bottle. And this is a piece of the powder pattern straight out of the stuff you buy. And there's extra peaks in here which correspond to the so-called superlattice reflections. And what's going on is that there's a fourth dimension which describes the offset of these extra reflections with respect to the sublattice. And if you plot the variation in, say, one of the sodium atoms in the structure along the y-axis as a function of this fourth dimension, you get this sinusoidal curve. And when you see it drawn out as a crystal structure and you allow the tau value, that's the fourth dimension, to vary, you can see this oscillation in the structure as a function of the fourth dimension. Okay? And I'll talk a little bit more about this tomorrow. So you can read in these incommensurate structures. You can actually do the fitting both in single crystal data and powder diffraction data to incommensurate structures. And you can also display what happens to magnetic moments when they're also modulated. And you get things that look like this, where the magnetic moments change as a function of the thing. This is something that happens, magnetism, fairly often. Right. And here's some more of these magnetic ones. These are rather spectacular movies that you can make in GSAS-II. And in this one, these things, there is also accompanying the magnetic oscillations, there is a structural oscillation. Here's the structure of cerium, ruthenium, tin that goes along with the magnetic one. Okay, capabilities. This is going to be a series of long tables involving lots and lots of different possible things to do. And there's a lot of stuff here. But the key thing is that these things that are marked with stars, there, and there, are all things that you can do in sequence for sequential data. And The other thing is that I sort of, these guys down here are the sort of really special sorts of stuff. One is you can compute, you can compute what the effect of a stacking fault is. Unlike BGMN, I think is what it was, there's no refinement possible. One day I'm going to go look at BGMN and find out how the heck he did it. But never mind. You can make PDFs, and you can also fit them using both large box models and small box models. A large box model is where you take the unit cell and you duplicate it sort of 10 times in all directions. You have a big box full of atoms, 10,000 or 15,000 atoms, and you allow them to jiggle around so that they fit the PDF, and then look at what the result is and try to understand why the PDF is reporting structural features that don't show up in the refinement. And if something which is brand new is the ability to do cluster analysis on powder diffraction data and on PDFs. So if you've got a lot of data and you want to know, sort of a real fast overview, what's going on, there's similarities between this data set and another data set. You can do the cluster analysis and that will show that to you, or at least that's the idea. This is new and under development. Single crystal data, basically, one of the things that sort of distinguishes GSAS-II from other software like c.l.s, for example, is that you can use more than one data set. All this will be on the web, so you don't have to take pictures. So you can do combinations of data, and people have used this to unravel site occupancy issues using single crystal data by tuning in on resonant wavelengths with a synchrotron to sort out how much iron versus how much nickel is on a site, for example. There's structure solutions by what I will call stochastic methods, which are sort of Monte Carlo type methods, and deterministic. And charge flipping is a deterministic method. Once you start it off, it just goes in its own path and comes to a solution, and I'll talk about that tomorrow. The structure and refinement is basically the same as what's for powder diffraction, and you can also do the stacking fault calculations. Small angle, it's basically all that one needs to be able to do for small angle calculations, including shapes of proteins. And I'll talk a bit about that tomorrow. Also, one can deal with reflectometry data. This is where you have a surface which you coated with something or other to a few hundred angstroms of something on top of silicon, say. And you want to know what that thickness is and does it mix with the other layers. Well, reflectometry brings in a beam at a very shallow angle, and you're looking at the slightly out of specular reflection, and you get oscillations. And this is what that's fitting. By the way, the code for GSAS-II, I told you it's 150,000 lines of code. 50,000 of it is dedicated to powder diffraction. Around 2,000 is dedicated to small angle scattering, and about 500 to this. Okay, this is a very simple problem. This is a simple problem. Repelt refinement is a complicated problem. And that tells you about, because the code and the amount of code tells you that. Okay, multiple data sets. This is simply picked out all the things that you can do with sequential fitting, to follow track something with a function of temperature, or pressure, or loading, or what have you. Tutorials. As I said, there were 50 of them or so. And what I suggest you do is, first of all, take a quick look at that first one, and that's only to describe how the user interface works. It's like one page. But the thing which you should do is to start with this one, which is fitting of X-ray powder diffraction data for fluoroapatite. And the reason is because every window is explained as to what it is that you have to do. And if you go through that one, even if it's a little boring, you will learn how GSAS-II works. Because the other tutorials will presume that you've done that one. So that it won't explain quite everything each time. The second one is a yttrium iron garnet constant wavelength neutron powder diffraction pattern. The issue there is the garnet has iron and aluminum on 2 sites, and what you're going to do sorting out is how much aluminum, how much iron. So you'll learn about how to do site constraints on atom positions to make them so that you can actually refine what the site fraction is. Scientifically, it had no value, turns out. This was a data set collected by Tony Cheatham 40-odd years ago, and he sort of looked at it and said, oh, this is an ordinary garnet. I didn't learn anything. But it's probably been the most refined neutron powder pattern ever, because it's part of the GSAS and the GSAS-II tutorials. And everybody does them. I always get the same answer, I think. 2 others of interest, depending on your thoughts. One is a combination of X-ray data and neutron data for lead sulfate. And the kicker here is that the 2 data sets were collected at different temperatures. So the lattice parameters are not the same. So the peaks are not in the same places, so which complicates the issue a little bit. And this one is what's used in the X-ray neutron summer school at Argonne and SNS. There's a combined fitting between X-ray data collected on 11BM and neutron data collected on PowGen. Other ones, there's a couple of ones for doing sequential fitting. These things are Rietveld refinements. They track parameters as a function of temperature, I think it is. For structure solution, there's a couple of these. One of them is, in order to solve a crystal structure for powder diffraction, the first thing you have to do is find out where all the peaks are, index them, and identify what the lattice is, and then work out what the space group is, and then you can go on and do the next step, which is to do charge flipping structure solutions or Monte Carlo structure solution. So that's what that's about. There's some modeling for stacking faults. There is the business about how you do image integration and calibration. And there's also some examples for small angle scattering and other ones. There's also a bunch of examples for doing magnetic structure analysis. But hello. I think that was it. I missed the thank you for some reason. Well, thank you anyway.
Any questions?
You'll have to shout because I'm deaf.
About the conic sections,
Sorry.
When you're calibrating the area detector, you discuss the conic sections.
Yes.
So yeah, when you tilt it to 45 degrees, I can see how that'd be a big distortion. But like, at what tilt are these other methods?
At what tilt is it sufficient to notice?
Yeah.
About a half a degree.
Oh, okay.
Yeah.
So that's
at a half a degree. One of the things that's plotted when you do the calibration is the center of each ellipse, and you can see them sort of track off in one direction or the other depending which way it's tilted. And what that tells you is how far the rings were offset, because of if you assumed the center of the ellipse was the right place. And once it gets beyond 1 pixel, it broadens the lines. And that happens at somewhere around 1/4 of a degree or a half a degree. So yeah.
so the users that we have that might use those other.
I would take all copies of Fit 2D and put them in there. With no apologies. Do they belong in there? They have not fixed that problem.
I have a second question. You showed how GSAS can do fitting for SACS data.
Yeah.
You know, like for refilled refinement, there's like goodness of fit criteria and WR. Are you aware of any such criteria for SACS fitting?
No, but I think I give you an R value.
Oh, okay.
I think there's a fitting value. It shows up on the console.
I just haven't come across.
Hmm?
I haven't come across an equivalent thing for powder diffraction. There's clear guidelines for what is.
Well, one of the problems with small angle scattering is you may not have noticed what the range of the intensities are, but it covers several orders of magnitude. So coming up with a sensible thing for quality of fit, which of course is nonsense, is a little tricky when the range of data covers 6 orders of magnitude, you know, from the top of that curve to the bottom of it. And the same thing with reflectometry.
You mentioned you've got a cluster analysis in there now. Do you have a tutorial for that? Or is it for the cluster analysis? Is there a tutorial?
No, not yet. There's no documentation, no tutorial. That's my next task, is to write that stuff. Also have to figure out what the hell it means.
Oh, sure.
Yep.
So in the cluster analysis, what has been developed so far? Just like criteria, like Snyder, like dissimilarity criteria.
Well, first of all, let me describe what the cluster. Well, I'll talk about the cluster analysis a bit tomorrow. But basically, each data set is a multi-dimensional vector. Okay, you know, they have 500 dimensions or 10,000 dimensions, depending how many data points there are. Okay, so what is the first thing you have to do is define what you mean by similar, and there's like a dozen different choices of how you compare one of these vectors to another. It could be the distance between their endpoints, it could be the angle between them, or it could be the correlation coefficient between them, and there's several others which have all been defined that I found in Python interface, basically. It's all uses Python. And then once you have that, then you have to characterize how those distances are clustered. And it will produce dendrograms, okay, and it will also do a principal component analysis on the distance matrix that you created to sort of show a 3D display of where the data points are relative to each other. And it also do a k-means description, which does it basically finds all those points which are closest to some mean value for a fixed number of possible clusters. You say, okay, I've got 5 clusters. It will then associate all the data with those 5. And color the principal component analysis plot accordingly. But I'm still trying to understand.
Yeah. Another question. So I found that there's part of GSAS that can prepare files for dysnomia for maximum entropy method. So does it like make all the files ready, and then you can run them? How does that work? It's like.
No, I think I've forgotten. Sorry.
But like this.
The Maxent stuff, that's for small angle scattering.
No. I think like.
There's somewhere else too. I've forgotten what it is.
I think it's just to make the structure more, to get like Fourier maps. Yes, right. That's to try to extend the information in the Fourier map to a higher resolution. So
it sometimes works, sometimes doesn't.
But we have to refine the structure first. And then
yes, you have to refine the structure first, generate a map, and then see if you can improve it using the Maxent method. Yeah, right. Okay, now I remember what we're talking about. As I said, any good idea out there is worth stealing and sticking it. With suitable references, by the way, put in every place, so that if you use any one of these special things, GSAS-II will tell you, please cite someone else's work, which is where I got it from. Yeah. There was something I was going to say. That doesn't matter. Okay.
A question regarding to the when you have a grazing angle measurement and you make a refinement in high rebuild, you also can maybe can make some correction about the texture, but you know that normally texture you need to have the diffraction vector in normal to the surface, but in the grazing angle you don't have that. How reliable is the information that you get from the texture in the rebuild?
Regardless of where the texture axis is, I assume you're talking about wire texture. Okay, even if it's perpendicular to the beam and the detector is here, it still affects the intensities on the that you actually see on the image, and they're going to be different from reflection to reflection. The model, you have to tell the model, okay, I've got a cylinder axis which is vertical, perpendicular to the beam. The one thing about texture analysis, you have to know, and I mean know, what the orientation of the sample is in the beam, because otherwise you can't make any sense out of the texture. So for instance, if you've got a rolled plate, you have to know what where the rolling direction is with respect to the beam in the experiment. And you have to tell GSAS-II what those orientation angles are so they can sort it out. Otherwise, it's just a jumble. Yeah, but yeah, even if the axis is not at the detector, it doesn't make any difference. You can still sort it out. Particularly for cylindrical texture, it's quite easy. For rolling direction, for rolled plates and things like that, it's more complicated. You have to have multiple sample orientations and multiple detector positions to sort it out.
I was just in thin films, you also make a grazing angle analysis to get more information of the cutting.
Yep.
And like
yeah, that's the reflectometer that I was talking about. Yeah. Now we don't do, unless my counterpart Brian Toby has been working on it, we don't do off-axis grazing incidence calculations. That's where you're looking at Bragg scattering in the plane. We don't do that. But this is simply layers of stuff, undefined stuff, on top of a surface. And what you can get out of that is how thick the layers are, and even if it's multiple layers, and how much mixing there is between adjacent layers. And also what the scattering power is on each layer. And that turns out to be important because one of the examples is a magnetic material in a polarized neutron beam. And depending on the direction of the polarization, it either scatters strongly or weakly off one layer in this stuff, and that changes the reflectivity. And the GSAS-II will sort out what that switch is. Okay.
I have one question.
What's that?
When you start the Rydberg refinement for OpenGSAS, you have to choose between Bragg-Ventano or the Weiss-Scherrer. It might be a follow-up of maybe what he was asking. What about when you measure powder diffraction with a constant grazing incidence angle and just sweep the 2 theta?
I'm not sure what we do about that. Yeah, I understand what you mean.
Because for a very thin film, you want to keep that incident beam really grazing all the time.
Yes, right. I think that's something that Brian has been working on, but I don't know where he's at with it. Yeah. Oh, yeah. That does bring up something I should mention about sample displacement. When you do a readbelt refinement, don't ever refine the 0 point on the diffractometer. It's 0. okay? Particularly a laboratory diffractometer, unless there's been somebody pounding on it, abusing your instrument, that 0 should be 0, because that's part of the alignment procedure when it's set up, is to make sure that 0 is 0. What's going on is what Joel referred to, is that the sample is displaced vertically, either up or down. And by the way, the sensitivity is on the order of microns. So it's not something that you can mechanically get correct by somehow manipulating it mechanically. It's always off by some amount. And as I say, the sensitivity is down in the micron range. One of my friends actually investigated this by putting shims underneath his sample and displacing the sample by known amounts. And it was a very expensive micrometer, but you could measure how thick the shim was. And he found one shim that was mismarked.
Oh.
So, yeah. And not only is that displacement significant, it's also accurate. It tells you exactly how much the sample has been displaced. And the displacement also applies to synchrotron data with cylindrical samples. There's a possibility of a sample displacement there, because the sample, if it's not at the center of the goniometer by a few microns, it will shift the peaks. 11 BM was a very high resolution powder diffractometer. Certainly the highest resolution powder diffractometer this side of the Atlantic, and maybe on both sides, I'm not sure. The sensitivity is down in the sort of 1 micron range. And I know from experience that if I have a powder pattern and I refine it without the sample displacement, I'll get an R value of like 10 or 12%. And as soon as I turn on the sample displacement, it cuts it in half. So a very, very significant kind of error or effect that one should take account for. Okay.
Any more questions?
So if you want to do the requirement, like using, so we have a mixture of, for example, 2 different crystalline phases with amorphous matrix. So we want to do the refinement to find the weight percentage of each phases. So can we do the refinement and find the exact value of each phases, or because of that amorphous matrix we can't have it?
Well, the amorphous material will not affect the phase fraction of the 2 crystalline phases with respect to each other. Okay. If you want to get at the amorphous content, the best way to do it that I know of is to spike the sample with a 3rd phase that has a known amorphous content, ideally 0. It should have roughly the same absorption quality as the sample. So if you're dealing with light element oxides, use alumina. If it's something heavier, then you have to be more selective. And then you get its phase fraction, and from the offset of the other phase fractions in that one, with respect to their original, you can tell how much amorphous material is in there. And don't be surprised if it's not a bigger number than you think.
Yeah, exactly. Because I tried to do that, and the values that I got, it's not really similar to what I started to.
Well, the reason why I make that comment is because if you think about scattering, just in general, okay, if you've got same kinds of atoms in an amorphous material as you do in a crystalline phase, then all the scattering power in the crystalline phase goes into the Bragg peaks. Okay, so they're very sharp, very high, okay, and very narrow. Okay, the amorphous material is then spread out over a very wide range and hides in the background. And 50% amorphous material is a shocking amount of how small that background is, because it's so spread out over so many scattering angles. Okay?
Yep.
Yep.
Well,
Did you have a question?
you sure?
You sure?
But if not, we can always ask later.
Yep,
We are a
absolutely.
little bit earlier, but if